Hello, I'm Mr. McBrien. This is TJ20 Network Hardware. Today we're going to talk about how we link computers together in terms of the hardware that we use. Ontario would like for us to be able to compare different kinds of networks, talk about LANs and WANs and peer-to-peer versus client-server, but also describe the basic components of a network. And that's what we'll take care of today. So let's start with the idea of design. How do we design a network? In fact, there's an entire discipline around this idea. Network administrators first collect requirements from an organization, establishing what the purpose of the network is, helps them define bandwidth, because if you ask users, they simply say, oh, it's got to be as fast as it possibly can be. In fact, in some cases, that's not necessary. They look at the budget, how much money is available, look at the number of users, the geographic locations involved, what security concerns there are with the data, how mobile the users need to be, this kind of thing. Now, depending on how dispersed the user base is, this will establish what kind of network we need. So the networks we tend to experience day to day are, in fact, a local area network where some computers are connected by a device like a switch or a router. So you have a LAN probably in your home. On the other hand, there may be networks the size of a city, like a Cogeco cable network. And these are typically groups of LANs. There can actually be larger networks than this, ones that sometimes cross borders from one country to another. So these wide area networks, well, an example of these would be ATMs. Now, what kind of hardware do we have that establishes these kinds of things? Well, let's start with the computer itself. It needs to have a network interface card. Now, desktops tend to have little devices like this plugged into an expansion slot, usually a PCI or PCI Express slot. And this will send packets of data from the computer to the network through an Ethernet cable. There are other kinds of networks, but Ethernet is pretty much what we see on a day-to-day basis. There are other kinds of NICs. Here's a wireless card, an old one for a laptop. But typically we're going to see something like this with an Ethernet port on it. So those Ethernet cables we talked about, well, they're not the only kind of network cable, but they are probably the most common for networks today. We call that kind of cable unshielded twisted pair, or UTP. And it's got 4 pairs of wires that are twisted together in order to give them better data transmission and noise cancellation properties. The connector, the plastic connector on the end, is called an RJ45 connector. And these kinds of cables will support star ring topology. And there are various types of these cables. You can call them qualities of cables, but really they're designed for something for more like bandwidth than quality is the better way to refer to it. So category 4 is pretty much out of date. There's category 5. In fact, it is also out of date. Cat 5e. And let's talk briefly about those descriptors then. So 10 base T, 100 base T, 1000 base T. Well, the number out in front means the number of megabits per second the wire can support. And so that 1000 base T is gigabit Ethernet cable. Now, in terms of range, all UTP is considered to have an effective length of about 100 meters. Longer than that, and you start to see tremendous loss of signal. Now, you can also run networks with coaxial cable. Bus topology requires this. It's pretty rare these days to see this other than for your television signal. One thing worth noting here is that you can have the best NIC in the world, extremely high throughput. If you connect it up with Cat4 cable, then it will be slow. The network speed is only as fast as the slowest component. Similarly, if you have a slow switch, it doesn't matter how good your NIC is or how good your cable is. Okay, so let's talk about some of those hardware components that move data around. Hubs were often used to connect computers and Ethernet networks. They use something called net buoy transmission, which means if they receive signal, they broadcast it to every one of the ports on the device. Now, hubs are extremely easy to troubleshoot. Essentially, because of the fact that they don't interpret the data in any way, they simply send information, shout it from the rooftops, if you will, each time any data comes in. And if one computer goes down, it won't even really notice. Hubs, though, aren't used, and the reason why they're not used so much anymore is because if two computers try to communicate at the same time, we see what's called data collisions. You can't broadcast both at the same time, and you start to see losses of data, and computers have to start sending the same data more than one time. For this reason, net buoy communication, a hub isn't considered to be an intelligent piece of network hardware. But it does serve us well to illustrate how the other pieces of hardware are better. So this is a switch. Good ones really aren't that expensive anymore, and so we see far more of these than hubs. How does it work? It's like a smart hub, where the hub broadcasts every signal to every computer. The switch is aware of which devices are on the network and sends information only to the destination computer. This increases the speed and efficiency of the network by reducing the number of collisions. By the way, the switch will also do a clever trick. It verifies what speed the devices on it can read data and will in fact slow down the communication when an out-of-date NIC is listening. And this again prevents data from having to be retransmitted multiple times. Now, you could ask yourself, wait a sec, how does the switch know where to send the data? How does it know which computer is expecting this information? And the answer is that the switch looks at all the devices connected to the ports, and it retrieves a MAC address for each one of those devices, and it creates this table, this dynamic table of MAC addresses. And since it knows which MAC address is on which port, it examines the data, called a frame, coming into the switch, and looks inside that frame for the destination MAC address. Then it opens the port only for that device. So this process of sending the frames through the correct port is called, go figure, switching, and that's what a switch does. And you might ask yourself, MAC address? What's up with that? So the media access control address is a unique identifier for an electronic device. It's assigned to it when it's manufactured. It's 6 sets of 2 digits or characters, and it's typically displayed in this form. 2 digits, a dash, 2 digits, a dash, etc. Every networkable device has a unique MAC address. Okay, so let's go through some of the rest of the hardware types. A bridge will divide up a large network into 2 different segments. It essentially creates 2 different networks. So why would you want to do that? Well, the answer is if you have too many workstations on a single system, your network is too slow. You get lots and lots of collisions, lots of confusion. What a bridge can do is connect 2 network segments together and decide which data needs to go to which segment of the network. And it reduces the number of collisions appropriately. Because it does it in this way, because it reduces the number of collisions, it'll speed up the network. You can think of it as being a 2-port switch, where it keeps track of all the devices on one port and keeps track of all the devices on the other port and decides which ones need which information. Now, there are other options of how to push data through a network. Routers are the most complex network hardware. They can connect LANs together, making WANs. So they can go ahead and locate workstations on a LAN, but they can also find networks on a WAN. The router will examine the data, check the destination address, find the most efficient route through the network, and then transmit the data accordingly. And so this reduces the number of collisions considerably. Now there's something else about routers, and that is that they're used a great deal in home networks, not because of this tremendous power to avoid collisions, but in fact because of a firewall effect we'll talk about in a few minutes. First, we need to understand how a router works. So a router will actually assign IP addresses to devices on its network. The router will examine packets, determine the IP address that is the appropriate destination for that packet, for that data packet, and send the packet to the correct location. Within a network, the difference between that router and a switch isn't all that important. So then you say, well, wait a second. What's an IP address? So an Internet Protocol address is a unique number that gets linked to your network activity. And the older IPv4 technology for IPs, IP addresses are 4 numbers between 0 and 255 separated by a colon. However, we have now begun the process of moving to IPv6 with 8 groups of 4 hexadecimal digits. Now, there's a big difference between a MAC address and an IP address. And that is that the IP address for a given device can change over time. In contrast, MAC addresses remain the same. Okay, other technology. For starters, I'd encourage you to remember that unshielded twisted pair cable has an effective range of about 100 meters. Anything beyond that, if you make a cable longer than that, the signal starts to degrade and may not be received properly. And you say to yourself, okay, well, but that's not very useful, because what if two buildings are further apart than 100 meters? What if I need to move data more than 100 meters? Well, there are a number of different answers to how to achieve that. But the simplest one is a repeater. A repeater will allow you to extend the range of your network by accepting the packet, much like a router does, rebuilding the whole packet, and then sending it onward. Now, what you want to do is you want to be able to describe the difference between amplifying and rebuilding. So we don't simply take the weakened signal and increase the intensity of it. If we did this, we'd increase the intensity of both the signal and the noise. And so any bits that were actually ones, but we're starting to get to the point where they might just be zeros possibly, well, they'd still be equally close to that being interpreted as a zero if we bumped them up. So instead, the repeater interprets the signal, and instead of multiplying it by, let's say, a factor of 3, it turns it back into a 1. So it's a logic-based system rather than a mathematical-based system. So the data coming out the other side is cleaner. Now, when it comes to talking about traveling long distances, you might start to ask yourself, well, what about speed of transmission? And in fact, eventually, as distances get longer, we become more and more concerned about the speed of travel of electricity across those distances. It doesn't much matter 100 meters, but when distances start to get longer, time becomes a concern. The good news is that instead of transmitting data across long distances using electricity, we can actually use light. So whereas an electrical signal would take a great deal of time to travel from Toronto to Tahiti, we can instead think about moving that information with a light-based signal instead. So, does anybody remember from science class, what's the speed of light? Well, the answer is in fact 300 million meters per second. And you might say, well, that's instantaneous. And in fact, it's not. But it's very, very fast. So if we could transmit information at that speed, then the time that it would take for a given bit to travel from Toronto to Tahiti would be 10,000 kilometers divided by, now we got to make sure we get our units right, 300,000 kilometers per second. And so if you take that math through, that means that that bit could travel from Toronto to Tahiti in about 33 milliseconds. So that, in fact, is quite quick. It's not instantaneous. And if you take a look at the extension for today, you'll see that it is far from instantaneous, but it is very, very fast. And this is where fiber optics comes in. So if we want to transmit to Tahiti using electricity, it would take a rather long time. Communication in fiber optics travels at the speed of light through strands of glass or plastic. This technology has been in commercial use since about 1980, and it is the least expensive way to send data across long distances. It's also very quick. You can easily achieve 100 gigabits per second. And for this reason, fiber optic cable now has been laying between each of the continents, and there are lines all between all major US centers. So you might ask yourself, why doesn't the light just sneak out of those fiber optic cables? In fact, fiber optic cables take advantage of a phenomenon called total internal reflection. That means that the light gets trapped inside the cables. Now, in terms of range, it's not unlimited. So fiber optic communication still has losses, still has distortion like electrical signals. So we fix these losses in one of two ways. We can have repeaters that work almost exactly the same way as in electrical signals. And we can have those amplifiers, because the signal's not as noisy. We can use amplifiers that are simpler, but can have accuracy issues. But it's a very different beast with fiber optics versus Ethernet cables. So long-haul communications can go up to 100 kilometers without a repeater or an amplifier. If we want faster speed, we'll put the repeaters closer together, but still much, much further apart than 100 meters. Now, communication across these long distances is rather interesting. Because the communication goes through many different routers, it is almost impossible to predict the path that data takes once it leaves your home or office. And we talk about a network cloud, because many of these devices in the background are making decisions about the best route for your data. So your data might go across phone lines, cable lines, through all kinds of different routers, but generally the path is completely unknown, and that's rather interesting. Okay, so for key points today, network hardware gets chosen based on cost and user requirements. Unshielded twisted pair cable, Ethernet cable, is still found throughout the world, despite its limitations in speed and range. Fiber optic is faster and higher range than electrical signals, but still has its own limitations. Hubs, routers, repeaters, bridges, switches, all these things have specific functions and capabilities that match those functions. We talked today a little bit about fiber optic communication and how fast it is, saying that in about 33 milliseconds we can transmit a bit from Toronto to Tahiti. As your extension activity for today, I'd encourage you to have a look at Flash Boys and read the free preview, or if you can get a hold of the book, go ahead and start reading it. And think about speed provided by fiber optics and how important that is. Certainly, the investigator in that book learned that the speed of networks can be extremely, extremely important. Okay, that's all for today. Thanks very much. Have a great night.